Hello friends, this video on DNF block elements part 22 is brought to you by examfear.com. No more fear from exam. Now let's talk about the magnetic properties. So magnetic property we know is mostly because of unpaired electrons in this atom. So this atom has a lot of electrons and sometimes you have unpaired electrons. We'll see the scenarios and that create this magnetic property, and this magnet is used in speakers mostly. And if you see the type of magnet, we have paramagnetic, diamagnetic, ferromagnetic, antiferromagnetic, ferrimagnetic. But we will be discussing more about the paramagnetic and diamagnetic. So in diamagnetic, it is repelled by applied electric field, and paramagnetic is attracted by applied electric field. This paramagnetic is actually attracted by applied electric field, and diamagnetic is repelled by applied electric field. Okay, so in paramagnetic, in diamagnetic, actually all electrons are paired. All electrons paired. Okay, and in paramagnetic we have unpaired electron. Since we have unpaired electron, they attract or they are attracted towards the electric field. In diamagnetic, all the electrons are paired, so they are not attracted toward the electric field. In fact, they are repelled by the electric field. Okay, and in fact there is something called ferromagnetic also. Ferromagnetic is nothing but glorified version of paramagnetic. Glorified version of paramagnetic, where they are very strongly attracted by the magnetic field, and they have permanent magnetic moments. So in fact ferromagnetism is, I will say, extreme case of paramagnetism, so we'll not discuss that. In fact, many of the transition metals are paramagnetic. Many of the transition metals are paramagnetic. Why? Because of the presence of unpaired electron. Okay, so we'll see this paramagnetic. So they told paramagnetism is nothing but due to unpaired electron, and they are attracted. For example, if you see this particular element is being attracted by the magnetic field, right? So they are attracted by electric field. And as I told, transition metals has, most of the transition metals has unpaired electron, and thus most of the transition metals are paramagnetic. Most TM is transition metals, they are paramagnetic, right? Now each unpaired electron has a magnetic moment. See, I'll tell you what is paramagnetic. For example, let's take manganese. The electronic configuration is 3d5 4s2. So if we draw the structure 1 2 3 4 5 s, 1 2 3 4 5 in D and 2 in S. So if you see, this is paired, this is unpaired. There are 5 unpaired electrons. Talk about titanium, 3d2 4s2, 4s has 2 electron. This D has 5, sorry, D has 2 also. So this has 2 unpaired electron. Okay, if we talk about this, suppose talk about nickel. Nickel is 3d8 4s2. So 1 2 3 4 5 4s2. 1 2 3 4 5 6 7 8, right? And S has 2 electrons. So if you see, there are 2 unpaired electrons here, there are 2 unpaired electrons, there are 5 unpaired electrons. So you'll see most of the transition metals has unpaired electrons, and thus they are paramagnetic. Now each of these unpaired electrons, each of these electrons has magnetic moment associated with its spin angular momentum also and orbital angular momentum, because these actually electrons, they spin like this and they move also like this. So both the spin and the angular momentum, that is spin angular momentum and the orbital angular momentum, both these actually has magnetic moment. Okay, so magnetic moment due to orbital angular momentum is not much, due to the movement is not much, but it is mostly due to the spin. I'm talking about the first series now. The first series, scandium, titanium, vanadium, chromium till zinc. I'm talking about the first series. So first series, my magnetic moment due to orbital angular momentum is not much. You can ignore that, right? So we'll talk about only the magnetic moment due to spin angular momentum. So you just think of a ball. When you throw a ball, when you spin it, the ball revolves and it moves also. Same thing, these electrons, they revolve also here like this, and they also move. Just like Earth. Earth has spin also, and it actually rotates also. It rotates and revolves. Similar to that, we have the electron also rotates and revolves. Okay, so the orbital momentum is almost negligible, but yeah, the spin momentum has values. And actually, if you want, you can find the value of the magnetic moment by formula mu is equal to n into n plus 2. Okay, when n is the number of electrons and this unit is bm, that is Bohr magneton. Right, this is magnetic moment due to spin of unpaired electron. This mu is magnetic moment due to spin angular moment. Okay, as I told, diamagnetic substance is the one which doesn't have any unpaired electron. Zinc is one example of transition metal which has no unpaired electron. If you see the electronic configuration of zinc, 3d10, 4s2. So draw this 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 2. See, it doesn't have any unpaired electron, so zinc is diamagnetic. Ferromagnetism is a strong form of paramagnetism, and iron actually shows ferromagnetism. We'll not discuss much into this. Now we'll see some of the magnetic properties. If you see a single unpaired electron, mu is equal to root of n into n plus 2. You'll put the values here. 1 into 1 plus 2, that is root of 3. That is 1.732 Bohr magneton. So single unpaired electron produces a magnetic moment of 1.73 Bohr magneton. Okay. So if you increase the number of unpaired electron, the mu also increase. So mu is directly proportional to unpaired electrons. Okay. So actually the observed magnetic moment that you can actually observe, this gives a useful data about the number of unpaired electron. For example, you see the calculated value, observed value are all matching for most of these. Okay. So it gives a fair idea of how the electron is, how the atom is, how many unpaired electron it has. Okay. And if you see here also we have a trend, it increased from left to right. If you go from scandium, titanium, vanadium, chromium, magnesium, iron, cobalt, nickel, copper, zinc. So it increases, right? And then decreases. If you see the calculated value also, it increases, maximum here, and then again decreases. Why? Because if we talk about the number of unpaired electron, we have seen that it increases and then it decreases. We have seen that, right? Same thing. So since the magnetic moment is dependent on the unpaired electron increase and then decrease in a given series. So the magnetic moment also increase and then decrease in a given series. Okay. Let's see some of the important compounds. For example, Fe3 plus and Fe2 plus. And both are paramagnetic, but Fe3 plus, if you see the electronic configuration, Fe3 plus will be 3d5 4s0. Fe2 plus will be 3d6 4s0. So this has 4 unpaired electron, this has 5 unpaired electron. How you can see? Okay, 3d5 in Fe3 plus, it has 5 unpaired electron. Talk about Fe2 plus, 3d6, 1, 2, 3, 4, 5 and 6. It has 4 unpaired electrons. Okay, so the number of unpaired electrons actually is more in Fe3 plus. So Fe3 plus is more paramagnetic than Fe2 plus. Similarly, if we talk about Cu2 plus, Cu2 plus is actually paramagnetic. Cu2 plus, if you see the electronic configuration, it is 3d9 4s0. So it has 4 unpaired electron. But if you talk about Cu plus, this is 3d10 4s0, and this is diamagnetic. Cu plus is diamagnetic, but Cu2 plus is paramagnetic. Okay, so it is not only that always copper will be paramagnetic or iron will be paramagnetic. So this is again, for a given iron, you have to find the electronic configuration, find number of unpaired electron, and then you can actually make out or confirm whether it's a paramagnetic or diamagnetic. We'll take some numerical now. The first question is to calculate the magnetic moment of a divalent ion, that is some ion in the aqueous solution if the atomic number is 23. So atomic number is 23, so for this it will be, for atomic number is 25, so for M plus, that M2 plus, it will be 23, subtract 2. Okay, so let's write the electronic configuration for this. For 23 number, 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s0. Okay, first write the electronic configuration of M first. This 25. So 25 is 2, 4, 6, 10, 12, 18, and this 2, 20, 25. This is the electronic configuration of M25. Okay, 3d5, 4s2, that is my manganese. So if we talk about of M2 plus now, it will be 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s0. The electrons are plugged from the 4s orbitals. Okay, this is the electronic configuration. So let's find the number of unpaired electron. 3d5, 5, 1, 2, 3, 4, 5. Right? So this has 5 unpaired electron. Since it has 5 unpaired electron, the magnetic moment is root of n into n plus 2. Put the value as 5, that is root of 5 into 5 plus 2, that is 5 into 7, root 35. The value is 5.92 Bohr magneton. Okay. So please first find the electronic configuration of a given metal and then find the electronic configuration of the given metal ion, and make sure that you pluck electrons from the s orbital, the outermost s orbital. Calculate the spin only magnetic moment for M2 plus where Z is equal to 27. Again, Z is equal to 27. We can actually write as argon. Argon will take care of 18. Then my 4s2, 20. Rest will be in 3d, 7. This will be the electronic configuration of Z27. Now we'll talk about M2 plus ions. So the electronic configuration will be 3d7, 4s0, because the 2 electrons will be plucked from 4s orbital. So let's find the unpaired electron in this 3d orbital. 3d7, 1, 2, 3, 4, 5, 6, 7. So number of unpaired electron is 1, 2, 3 here, 3. So mu is what? Root of n into n plus 2. Put the value of n as 3. 3 into 3 plus 2, that is root of 3 into 5, 15, and that is nothing but almost 4 magneton. Less than 4, 3.9 almost. This is the value. Okay.
Thank you. Visit examfear.com to watch more videos, attempt free online tests, get free study materials, find tutors and mentors, and much more. Thanks once again.